You're listening to Worth Electronics' What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our very own Worth Electronic technical specialists who are going to shine a light on interesting topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics' What's Up podcast. Today we're going to be discussing a very common component, but sometimes it gets easily overlooked. We're going to give insight into the current sense resistor, and we're going to talk about how to evaluate some of the specifics of the component, such as details in the datasheets, different measurements including the rated current, and we'll also talk about the equivalent circuit model and advantages of wide terminal.
My name is Frank Puhane, and I am with Worth Electronic now more than 8 years. I'm in charge for the technical engineering for capacitors and resistors, which includes design-in support, measurements, and customer support. Talking about a resistor is not the most attractive topic, I know, and often there is not much time to go in detail about the specification of different resistors. This is why we named our presentation a look behind the scene of current sense resistor to give you a more detailed insight. We will have a short overview about the current sense resistor itself, about the basics, and go further into all the details in the datasheet, like resistance, voltage, current, temperature coefficient, degrading curve, and so on. The measurements have a big impact on the provided data, so we will have a look how the data is obtained. Here we will have a close look of the definition, especially for the rated current. Of course, in every application, there is some kind of frequency. Fortunately, we live in a real world, but unfortunately, we have to deal with the real components. Resistors have some frequency behavior too. And simulation is an overall topic, so we will have a closer look to the equivalent circuit model. And last but not least, we will have a short look into our well expert. When we are using a resistor within the circuit of the application, we want to make the current measurable. This resistor is also called shunt. The current through such a resistor generates a proportional voltage drop according to Ohm's law. And normally, very low resistant values are used to generate a really low voltage drop up to a few hundred of millivolt. In case of low currents, a very precise resistance value and an amplification circuit have to be used to get stable measurements because of the very small voltage drop we get. But in the end, it's all related to Ohm's law. Besides the resistors, there are some more possibilities to measure the current. So how can we choose the right sense principle? To select the proper principle, we have to answer some questions. I listed for the following questions. So first, what type of current should be measured? AC, DC, or both? What is the current range of the measurement? Low current, high current. What is the accuracy you need? Is the TCR important? So the change over temperature. Do you need an isolation within the application? And then based on these answers, you can choose between special current probes, special sensors like Hall or magnetorestrictive, also flux gate, and we have our current sense transformer. And of course, you can use our current sense resistors. Of course, there are two more ways I would like to show. One is the current sensing due to the RDC of the inductor. So this is the picture here. Because inductor are also real components, you have some resistance from the winding, and you can use this to measure the current. And you can do some current sensing due to the address on of the MOSFET. you can monitor this, and then you can get also the current which is flow in the application. When you search for different types of resistors, you will get a lot of results. Of course, we have THT and SMT. It doesn't matter on which technology tree you are looking. There are different types available. A more common one is the SMT, rectangular and metal resistor. More precisely, the thick film and the metal plate. The thin film distribution is massive, but for current sense, we will stick to the metal plate and thick film resistor here. Now you can imagine what kind of products we have in our portfolio. Of course, metal plate and thick film current sense resistors. There are some differences now what I would like to point out to provide you a more detailed insight. Our thick film resistor are named WRIS KS, XS. So XX stands for the different match code series we have. These resistors contain a stable substrate coated with a thick metal film. After the coating, it gets trimmed to the right values, what we want to have. There are normal or white terminals available, and compared to other technologies, they have higher tolerances, but are lower at the price. Then the metal plate resistor are named WRIS PSMX. These resistors have a metal plate body, such copper alloy or ferrochrome alloy, or also some kind of manganese alloy. One advantage is the high power capability. They have also good temperature characteristics. Also, the linearity is quite good and have a high accuracy. Also here, normal or white terminals are possible. And they are quite robust because of the more or less simple production process. Now, we want to give you more insight about the resistors. We want to talk about information in our datasheet and to show you that there are really some key points to consider. There is more to say about a resistor than people might think. You can find the datasheet through our online catalog within our homepage. In our case, we selected our high performance WRIS PSMC resistors. It is then easy to access the datasheet also for each single part itself, so from the same series. And there are also other downloads available. So with the fields here, you see there are more than 6 files available. There are 3D files, simulation files, and PCB libraries, and so on. You can also have access to it via our homepage. We are going to talk in detail about what all these parameters and why they are important when you select your component. First, the main electrical properties like resistance, rated power, and so on. Then the other general and ambient operation properties like operating temperature and also then temperature rise. And at least we check the performance of the size and form of the chip resistors. Here, especially the key point of a white terminal. The primary characterization is, of course, the resistance value. We see in the red rectangle that the resistance is 100 milliohm with a production tolerance of plus minus 1%. The value is measured at a defined laboratory condition, like a specific temperature around 22 degrees or 25 degrees or 20 degrees. The measurement device can really vary depending what is available in your lab and what kind of resistance range you expect. High values can be measured easy with an, low-cost device like here in the left picture. Here's a 47 ohm type. When more precision is needed, there are different devices available, like an LCR meter here, and of course some milliohm meter, where you can really make accurate measurements in the milliohm regions. Just a little reminder for the next slides, Ohm's law describes the relation between voltage and current. The power definition and the power limit is an essential characteristic for the current sense resistor itself, due to the fact that we want to make the current measurable with a voltage drop over these resistors. We will also generate heat inside the component. In our case, we have this 100 milliohm and a power rating of 1 watt. With the defined pad geometry, like you see in the gray picture here, so for the land pattern, we can measure the temperature rise with a certain current flow through the duct. When we reach the specification, here we go up to 70 degrees. We have then our rated current with full load. With this current, we then can calculate the rated voltage. As you see here, we have the 0.31 volt. The power loss equation defines the relation between the current and the voltage. So we can increase, for example, the voltage when you go down with the resulting or the rated current. Higher currents have to be checked because this depends, like always, on the applications and the layout of the PCB. There is a short time overload condition of the voltage around 2.5 times. Also for the current, 2.5 times for as a maximum 2 seconds. So you have to really be careful with overload conditions. And there's an dielectric strength of the material too. So when you need more details here, please get in contact with us and we can have a look. Because the power limit is an essential topic, we go more in detail here. To demonstrate the importance of the layout, we did some tests in our lab. From the rated current definition of our inductor, we have some knowledge and also some standardized definition of the rated current. So we have special PCBs. This is defined in the ISE 62024-2. All PCBs you see here in the picture have a copper of 35 micrometer. And when we're going from top to the bottom on the left side, we have here our 2 ampere version of the rated current board, then 3 amps, 7 amps, and at least here with also a lot of wires, a 22 amp version. When you expect the higher currents, we have some, of course, pure copper PCB, like you see here on the right picture at the bottom. When you have a closer look, you see also the resistors already mounted on some PCBs. They are painted in black to have a better temperature measurement. To have a better overview about the results, we created some diagrams. So the first measurement was with the 3 ampere PCB. Because we cannot transport enough current and the heat dissipation is not really right, we only get the 16 amps at 120 Kelvin temperature rise. Then we use the other board with the 22 amp, so bigger copper traces, more wires. We can enlarge our rated current up to 25 ampere. We stopped at 110 Kelvin temperature rise, and at least we use this pure copper PCB with a big copper layer, and we can get to our 32 amp rated current, but still with more temperature rise than defined in the standard, as you see here in with the arrows and the circles. There is some difference where you then define the rated current. My colleague Eliasar designed a real-life example. This PCB demonstrates a SiC gate driver with our WE-AGDD. So it's a special transformer. The key feature of this design is the required board space of the gate driver. When you want to have more information, please follow the link, and there we provided, as I said, more information. Within this demonstration, there's also a resistive load built up directly on the PCB. For this purpose, he used our SiC film resistor, so WRIS-WKB. It's a white terminal part with 1225. The resistors are connected in series. To see the heat generated, we use a thermal camera in this case. When we're operating at full load, we see that the resistors, they got really hot. Compared to the PCB region, we have a difference of around 20 Kelvin. So the PCB gets around 65 degrees. And when you have a look at the middle of the resistors, here it's 95 degrees. Then if you consider this series connection, please be aware of the different temperature of the parts, what you see on the right picture here. The thermal distribution is not equal for each part. The parts in the middle here gets the most thermal stress with around 96 degrees. Please keep in mind that the temperature of the SMD resistor is strongly influenced by the layout and also the surrounding components, and of course the PCB itself. So this has to be considered when placing these resistors really near by each other. Going further to the electrical specification, we will talk about the TCR, so the temperature coefficient of the resistance. It is an important parameter for current sense resistors, even if it's widely ignored for resistors in general. In the most electronic components, the electronical characteristics vary a lot with the temperature, and conductivity of the material is one of the properties with a high dependency. But if we are to measure current using the resistance, we need the value to be stable along a wide temperature range, because we are going, as you see already in the last slide, going to warm up the resistance when we're operating it. The current sense resistor with very low TCR, like 100 ppm per degree Celsius, have different metal alloys that combine positive and negative TCR to balance the combined resistor itself. So if you want to estimate how accurate is your current measurement, it will be at best as precise as the resistance value of the resistor. You have to take into account both the resistance tolerance and the TCR, and see which one will be a bigger factor in your accuracy. For that, it is good to know how much will the component heat up and calculate the worst case with our TCR parameter. In this example, our 10 milliohm part has 1% tolerance, and we calculate what happens if we heat up with 90 degrees hotter than the ambient, and calculate the impact of the TCR of 100 and 350 ppm per degree Celsius. So with the 100 ppms, we still don't have a big issue, because the resistance deviation because of the heating is still less, and the tolerances went with the tolerances. When we have a look at our 350 parts per million change, we might run into problems if we ignore how warm will the resistance get. In this case, the deviation because of the temperature is more than 3 times the possible deviation from the tolerances. Yeah, now we will plot some similar case to make the TCR visible for you. On the left side, we have an 100 milliohm and 1% tolerance SiC film resistor. On the right side, we have a 10 milliohm and also 1% tolerances. The blue rectangle shows where we expect initial values to be, like the production tolerances, and the orange triangle shows how much the resistance could deviate with temperature different than here, especially 25 degrees Celsius for the laboratory measurement. For the left resistor, we have 250 ppm, and for the right, we have our 100 ppm. What you see here in the diagram is a really big effort, but we measured the real TCR for various parts in our lab in Berlin. We choose the thick film, a metal plate, wide and normal termination. And depending which TCR the article have, you see the diagram, what I explained one slide before. So the theory and reality matches, fortunately. If you want to have more information like this, please get in contact with us or follow the link to our web expert. About it, the rating, you may have seen this in the datasheet before, that the operating temperature is stated up to 155 degrees. But again, if you look in detail, there is another specification in the datasheet, the derating curve of the rated power. Regarding the limit of having too much current flowing when the ambient temperature is already too high and the heat energy may not be extracted for safe functionality and stability, the terminal part temperature, which reflects Schatz's influences accurately, is more suitable as a reference for the power rating of the resistors. When you monitor the temperature of a terminal, it prevents the part from damage and allows to select the proper size and number of needed resistors for your application. So this is really worth to do to not only check maybe a hotspot of the part, but to monitor the complete terminal temperature rise. Very often we get asked how do our resistors behave in higher frequencies. Of course, the resistance value as stated in the datasheet is measured with DC voltage and also current, DC current. This is enough for the most resistor applications. From most manufacturers, you don't get much information about impedance when we understand the impedance like a resistance of the AC voltage. Same as with inductors and capacitors, because resistors are not ideal components, we have the parasitic effects that change the impedance across the frequency spectrum. To prove our statement, please have a look at the picture on the right side here. This is a 10 milliohm resistor. As you see, beginning from 1 megahertz, the part starts to act like an inductor. And here we assume or measured around 1 nanohenry parasitic inductance. So this limits the frequency range where we can use the current sensor resistor as an sense. So how do we do the measurement? So we do it with a tube with a VNA. So any two-port network analyzer can be used to measure this impedance spectrum, which is a really advantage because they are more affordable than a real impedance analyzer. Of course, some complex calculation must be performed here. We placed here the formulas, and if you need to help to understand it, just get in contact with us because there is really no time to go in detail here. In this picture, you can see our measurement setup. So these are the DUTs. And with the standard we use to correct the test PCB and connectors out of the measurement. So we do a really good calibration. There are, of course, some limitations of this method. So with the shunt through method, we may run into problems for resistance lower than 20 milliohm if the frequency is lower than 100 kilohertz. Resistors higher than 1k ohm should be measured with a similar process. called two-port series through measurement. It's also the same with inductor measurement. What you can see here in this diagram, you can see some examples from our lab, also measured here in Berlin, Germany. We measured 6 different resistors of the same size and 6 different resistance value. We go from 100 milliohm up to 10k ohm, so like a multiplier of 10. In the 10 kilo ohm case, you can see the stability of the measurement is not adequate. Over 20 kilo ohm, the measurement is impossible with this kind of method, so like with the shunt through method. So depending on what kind of impedance you expect, you have to select a different measurement method. This is really important to don't get crazy with the results. So after we have seen the measurements, we may want to create, of course, a model to describe the non-ideal behavior, also to use it in different simulation tools. But we have seen clearly 2 different trends. For high value resistance, we can see that at high frequency, the degrees of impedance, so this kind here. This is the parallel capacitance taking over as a low impedance path. Sorry, this was this graph here. I'm sorry. Of low impedance path of the AC signal. If we look at a low resistance case, when we increase the frequency, we can see the impedance increase. This is series inductance that produce a higher impedance in the same path as the resistor. And also this is the same way our ferrites work in the application. If you want to create this equivalent model for any resistor, we can combine those 2 behavior in one model. In this example, we created a model with the following parasitic components. So the series inductance is 1 nanohenry, and the parallel capacitance is 0.1 picofarad. This model was created observing several 0805 resistor measurements over the same family. Then we simulated a frequency characteristic with different resistance values and same parasitics. As you can see, the behavior corresponds perfectly with our measurement. Also interesting is the self-resonant point. So what you see here, this is correspondence with our measurements, and this is here the self-resonant frequency. When you see it's around 16 gigahertz in this example with very realistic parasitics, we are working to make all models available to you as soon as possible. So please get in contact also with us if you have a specific request for impedance measurements. I already talked before about a wide termination resistor. Common or regular chip components have the terminals in the short edges. Resistor manufacturer with the terminals in the long side are then called the wide terminal. This brings several advantages to this kind of products. We have a larger copper contact surface with the PCB, which results in a higher rated power, for example, 3 watt for 1225 instead of 1 watt for 2512, and a higher mechanical robustness because we have a higher solder layer. Another advantage is the frequency behavior. Due to the longer pads and shorter gap between the pads, we have a lower ESL, also due to the shorter length of the resistive element. And this means the resistor will stay pure resistive up to a higher frequency range. To clarify this behavior, we made a simulation with LT-SPICE here. What you see in the left diagram is a simulation of a 100 milliohm resistor. with a fixed parasitic capacitance of 1 picofarad. As a model, we use the simple resistance model like I showed in the previous slide. Now what happens when you change the parasitic inductance? It's like with the small ceramic capacitors, so with the MSLC, reducing the ESL will lead to a shift of the resonant point of the device. And here we are going from 1.5 gigahertz for a 10 nanohenry ESL to around 1.5 terahertz for 1 picohenry. Yeah, of course. Yeah, this is probably not important for most of the current sensing applications, but it is always important to be aware of the limitations of some critical components. I would like to remind you that you can also find all of these technical parameters of our resistors in our online tool RedExpert. This is the best resource for developers who want to visualize the technical characteristics and use the table to compare and select the components. At the moment, there are the basic specification like measuring voltage and rated power available, but we are working on more specific data like rated current, pulse capability, and so on. So please step by time to see what's new here. Yeah, what we not cover today is the topic of especially the pulse capability. There are several information which varies from different vendors. We can provide such data based on the specification of your pulse. So when you can give us your specification, we can check exactly the behavior. So currently we are working on to bring this data on in our online tool. So there is continuous and of course in single pulses. The current noise or the Johnson-Nyquist noise has a direct relationship to the type of resistive materials. The noise is mostly expressed as S in dB, and sometimes there is also a pulse voltage defined. This is linked to the dielectric withstand voltage and is dependent on the pulse duration. In most cases, the nonlinearity describes an attenuation of the third harmonics in dB. This may be important then for the EMI measurement. And we will try to provide this kind of information in another webinar or a document as soon as possible to provide you more information.
Components available at Worth Electronic online. And for any questions, simply click the icon to talk with our live chat team. To view the materials and replay the video, visit us online at www.we-online.com/podcast. You're listening to Worth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists. We're going to shine a light on interesting topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast.